Tonight, something you have seen 1,000 times and never actually seen at all. Picture the solar system. You know the image. The sun in the middle, the planets on their rings, the whole arrangement laid out below you like a diagram, viewed from somewhere above. It is on the wall of every classroom on Earth. It is in every textbook, every documentary, every app, on every phone. And here is the thing almost nobody realizes. Every single one of those images is a drawing. Not one of them is a photograph. There is no photograph of the solar system seen from above. There never has been, and no human eye or camera has ever occupied the position that picture is taken from. We have photographed the surface of Mars and the rings of Saturn from inside them, and a comet's nucleus from a lander sitting on it, and a galaxy so distant its light left before the Earth existed. We have never once managed to get far enough above our own solar system to take its portrait, and the reason is not distance, and it is not money, and it is not that nobody thought of it. The reason is that we live inside a disk, and getting out of that disk even slightly is one of the hardest things in all of spaceflight. It costs more energy to climb straight up out of the plane of the planets than it does to fly all the way to Pluto. Tonight, we are going to look at the direction we never look, straight up and straight down, out of the flat sheet that holds everything we have ever known. And we are going to meet the 3 machines that actually made it out and see what they found waiting up there. Now, let's begin. Before we start climbing, settle in. Let the weight of the day go out of your shoulders, let your jaw unclench, and let your breathing find its own slow rhythm without any help from you. Perhaps the lights have been off a while. Perhaps you are somewhere on a long night waiting for it to be over. Wherever you are, as you listen, this is a good place to be, and nothing here needs anything from you. Tonight is a slow climb in a direction nobody thinks about, and if sleep takes you part way up, that is exactly what it is for. Let us begin with the shape of the thing, because it is the fact everything else tonight depends on, and it is easy to know without ever quite feeling. The solar system is flat, not roughly flat, not flat as a convenient approximation, genuinely, remarkably flat, to a degree that would look almost artificial if you could see it. Every one of the 8 planets orbits within a few degrees of the same plane. Mercury is the wanderer, tilted about 7 degrees from Earth's orbit, and the rest are far more obedient than that, most within 2 degrees. If you built a scale model of the solar system with the orbit of Neptune the size of a football stadium, the entire vertical thickness of the planetary system, the whole distance from the highest point any planet reaches to the lowest, would be smaller than a few feet, a stadium wide and a couple of feet thick. That is our home. It is not a swarm, it is not a cloud, it is a sheet. Astronomers have a word for that sheet. The plane defined by Earth's own orbit is called the ecliptic, from the ancient observation that eclipses happen when the moon crosses it. And you can see the ecliptic with your own eyes tonight, without any equipment, which is one of my favorite facts in astronomy. Go outside and find the planets. Venus, Mars, Jupiter, Saturn, whichever ones are up. They will not be scattered randomly around the sky. They will all be arranged along a single arc, a line running across the heavens, and the moon will be on that line too. And the sun travels along it during the day. That arc is not a coincidence, and it is not a pattern our brains invented. That is the plane of the solar system, seen edge on from a position inside it. Every night of your life you have been able to look up and see the flatness of your own solar system drawn across the sky as a line, and probably nobody ever told you that was what you were looking at. And the reason we see it as a line rather than as the beautiful spread out diagram from the classroom wall is simply that we are in it. We are inside the sheet. We have always been inside the sheet. Earth sits in that plane. We evolved in that plane. Every telescope we have ever built has observed from within it. And every spacecraft we have ever launched began its journey already moving along it at enormous speed. To see the solar system laid out flat, the way it appears in every illustration, you would have to be somewhere no human object has ever properly been, above it, looking down. So why has nobody gone? This is the heart of tonight, and the answer is one of the most counterintuitive facts in spaceflight, so let us take it slowly, because once you have it, the whole shape of our history in space suddenly makes sense. Start with a fact about where you are sitting. The Earth is going around the Sun at about 67,000 miles per hour. That is not a figure of speech, and it is not gentle. You, your bed, your house, the ground under it, the entire planet is traveling sideways through space at roughly 19 miles every second, and it has been doing so your entire life, and you have never felt it, because everything around you is moving too. Now here is the crucial part. When we launch a spacecraft from Earth, it does not start from rest. It inherits all of that. Every rocket that leaves this planet is already moving sideways at 67,000 miles per hour before its engine does anything at all, because it was standing on a world that was already doing that. The rocket's own work, the enormous flame and the thousands of tons of propellant only adds a modest amount to what the Earth has already given it for free. And that inheritance is the trap, because it is sideways. If you want to travel outward to Mars or Jupiter or Pluto, you are working with that inherited motion. You add a little speed in the direction you are already going, and you climb the sun's gravity to a wider orbit. It is efficient, it is what every planetary mission does, and it is why we have visited every planet in the solar system. But if you want to go up, out of the plane, you are not adding to that sideways motion. You are fighting it. You have to cancel it. To end up in an orbit going over the sun's poles instead of around its equator, you must somehow shed nearly all of that sideways 19 miles per second and replace it with the same speed in a completely different direction. Work out the arithmetic and the requirement comes to something on the order of 94,000 miles per hour of velocity change applied by your own engine. That number is worth sitting with for a moment because it is not a difficult number, it is an impossible one. It is far beyond what any rocket humanity has ever built or seriously designed could deliver to a useful payload. Going to Pluto, the most distant object we have ever visited, needed a small fraction of that, which produces the sentence that gives tonight its shape, and it is completely true. With the propulsion we actually have, the space directly above your head, a few 100 million miles straight up, is harder to reach than the outer edge of the solar system. So the space above the plane is not unexplored because it is far. It is unexplored because it is expensive in the one currency spaceflight cannot cheat. Except that spaceflight has exactly one way to cheat, and every story tonight turns on it. You cannot buy that velocity with fuel, but you might be able to steal it from a planet. The technique is called the gravity assist, and it is the single most elegant idea in the history of space navigation. Here is what happens. A spacecraft falls toward a planet, swings around it, and flies away again. From the planet's point of view, nothing has changed. The craft arrived at a certain speed and departed at exactly the same speed because gravity gave back on the way out precisely what it took on the way in. But from the sun's point of view, something enormous has happened because the planet itself is moving. The spacecraft has effectively grabbed hold of a moving object and been flung, and the direction and speed of its travel around the sun can be changed completely. The energy comes out of the planet's own orbital motion, which slows by an amount so unimaginably small it could never be measured, because the planet outweighs the spacecraft by a factor with more zeros than anyone needs. That is how everything far away gets visited, and crucially, a gravity assist does not only change your speed, it can change your plane. Approach a planet from the correct angle and it will throw you upward, out of the sheet, for free. The one thing our rockets can never afford, a planet will do for nothing. If you arrive at exactly the right place at exactly the right moment, having planned it years in advance. So, the question of who has ever left the plane of the solar system turns out to have a very short answer, and it is a list of vehicles that got a planet to throw them. But before we meet them, we should be precise about what the plane actually is, because there is a lovely subtlety here that most descriptions skip. We have been talking about the ecliptic, which is the plane of Earth's orbit, and it is the standard reference because we live on Earth and it is convenient. But there is nothing special about it physically. Earth is a small planet. If you want the true structural plane of the solar system, the one the whole system actually organizes itself around, you have to ask what the system's total angular momentum is doing. And that is dominated not by Earth, but by the giants. Jupiter alone accounts for the large majority of the orbital angular momentum of everything that circles the Sun. So astronomers define a different reference, called the invariable plane, which is the weighted average of all the orbits. effectively the plane defined by the whole system's spin. It sits a little over 1 degree away from the ecliptic. Small, but it means that Earth's orbit is itself slightly tilted relative to the true midline of the family it belongs to. Even our definition of flat is parochial. We measure the solar system against ourselves and are gently, permanently, 1.5 degrees off. And it is called invariable for a reason worth knowing. Individual orbits wobble. Over tens of thousands of years, the planets tug on each other, and their orbital planes tilt back and forth by small amounts, and Earth's own orbital plane drifts. But the sum of everything, the total angular momentum of the whole system, cannot change, because there is nothing outside to change it. So, the invariable plane stays put while everything shuffles around inside it. It has been in essentially the same orientation since the solar system formed, and it will hold that orientation until the sun dies. Of all the reference lines humanity has drawn across the sky, that one is the closest thing we have to a permanent fact. Now, why is any of this flat in the first place? Because a sheet is a strange shape for gravity to produce. Gravity pulls equally in all directions, so the natural thing for a cloud of matter to become is a ball. The sun is a ball. Every planet is a ball. Why is the arrangement of the planets a disk? The answer is one of the most satisfying pieces of physics there is, and it explains the shape of an enormous amount of the universe. Start with the cloud that made us, a vast, slow drift of gas and dust, several light years across, cold and dark. Somewhere in it, a region begins to collapse under its own weight. As it falls inward, it does what everything does when it falls inward, and has even the tiniest amount of rotation to begin with. It spins faster. This is the ice skater pulling their arms in, and it is not a metaphor, it is the same law. Angular momentum is conserved, so as the radius shrinks, the rotation speeds up, and a cloud that was turning imperceptibly over millions of years begins to turn seriously. Now watch what that does to the shape. Along the axis of the spin at the top and the bottom, nothing opposes gravity, and material falls straight in. But out at the equator, the rotation is throwing material outward, resisting the collapse. So the cloud falls in freely from above and below, and only slowly from the sides, and inevitably, over a few 100,000 years, the ball becomes a lens, and the lens becomes a disk. Meanwhile, inside the disk, particles on tilted or eccentric orbits keep colliding with each other, and every collision averages out the differences until everything that survives is going the same way, in the same plane. Flatness is not a coincidence. Flatness is what spinning collapse always produces, and it is why Saturn has rings rather than a shell, why spiral galaxies are disks, and why the accretion disk around a black hole is a disk. The universe makes sheets whenever it makes something out of a spinning cloud, which means the emptiness above and below is not an absence, it is a scar. It is the record of where all the material fell out from 4.5 billion years ago, on its way to becoming the plane we live in. Everything that was ever up there came down. That is why there is nothing there now, and that gives us the honest answer to what a spacecraft flying above the plane would actually find, which we should be clear about before we start celebrating the ones that went. It would find almost nothing. No planets, obviously, very little dust, because the dust is in the plane too. Fewer asteroids and comets, though not zero, since the Oort cloud is genuinely spherical, and the scattered disk objects ride steeply tilted orbits. Mostly it would find the solar wind and empty space and a completely unobstructed view. But that word, unobstructed, is doing more work than it appears. Because the one thing you get above the plane that you can never get from inside it is the view. There is a wrinkle in the flatness that almost nobody mentions, and it is one of the genuinely unsolved problems in our own back garden, so it belongs here before we go any further. The sun is tilted, not the planets relative to each other, which we have covered, the sun itself. Our star rotates once every 25 days or so at its equator, and the axis it rotates around is not perpendicular to the plane of the planets. It is off by about 7 degrees, which means the sun's equator and the plane in which everything orbits are not the same plane. They are tilted with respect to each other permanently by a small but perfectly measurable amount, and that should not be true. Remember where the flatness came from. The sun and the planets condensed from the same collapsing, spinning cloud. The sun formed at the center of that cloud from the same material spinning in the same direction for the same reason. Its rotation and the planet's orbits are both expressions of the original angular momentum of one single object. They should be aligned. The star should spin in the same plane its planets orbit in, because both inherited that plane from the same source at the same time. 7 degrees is not a rounding error. It is a genuine discrepancy that has been known for a long time and explained for none of it. Something tilted either the sun or the disk, relative to the other, and nobody knows what. There are candidate explanations, and they are all interesting. One says the sun was born in a crowded cluster, as most stars are, and that a passing star came close enough early on to talk the young disk out of alignment with the star at its center. Another says the culprit was internal, that a misalignment between the young sun's magnetic field and its disk did the work over millions of years. And a third, which got a great deal of attention when it was proposed in 2016, is that the tilt is the fingerprint of something we have not found yet. If there is a large undiscovered planet on a distant inclined orbit far beyond Neptune, its gravity acting over billions of years could have slowly torqued the entire plane of the known planets, tipping the whole system relative to the sun. On that account, the 7-degree tilt of our star is not a fact about the sun at all. It is a shadow cast by something out in the dark that we have never seen. I have no idea which of those is right, and neither does anyone else. But I love that it is sitting there because it is a reminder about tonight's whole subject. We have been describing the plane as the fundamental structure of our home, the thing everything is organized around, and it turns out that even the plane does not quite agree with itself. The star is at one angle, the planets are at another, The invariable plane, the true average, is at a third. There is no single flat surface you can point to and call the floor of the solar system. There are three, all slightly different, and the discrepancies between them are unexplained, which is a rather good description of most things in astronomy once you look closely. From a distance, an elegant, simple structure. Up close, the elegant structure is a family of approximations that disagree in the last few degrees, and the disagreements are where all the interesting questions live. So when we say tonight that nobody has ever seen the solar system from above, there is an additional, small precision worth having. Above what, exactly? Above the ecliptic, which is Earth's own orbit and therefore a parochial choice. Above the invariable plane, which is the honest, structural midline. Or above the Sun's own pole, which is tilted 7 degrees from both. Solar Orbiter is climbing toward the Sun's pole because it is studying the Sun. A mission that wanted the classroom photograph would want to be above the invariable plane instead. They are not the same direction, and the difference is real, and there is something quietly funny about the fact that our solar system cannot even agree on which way is up. So let us meet the first one out, and it is a spacecraft you already know, which did something almost nobody realizes it did. Voyager 1 was not designed to leave the plane. It was designed for the grand tour that once in a 176-year alignment of the outer planets, and its assignment was Jupiter and then Saturn. But inside the Saturn encounter, the mission planners faced a choice, and it is one of the great decisions in the history of exploration, and it was made deliberately, knowing exactly what it would cost. Saturn has a moon called Titan. In 1980, nobody had ever seen its surface because Titan is wrapped in a thick orange haze, and it was known to have a substantial atmosphere, the only moon in the solar system that does. It was the single most intriguing object in the outer solar system. And the geometry of the encounter meant that a close pass at Titan required a trajectory that would bend Voyager 1's path sharply, up and over Saturn's south pole and out of the plane of the solar system entirely. Taking that trajectory meant the spacecraft could never visit another planet. Uranus and Neptune would be permanently out of reach. The grand tour for that spacecraft would end at Saturn. They took it. Titan was judged worth more than 2 more planets, and Voyager 1 flew close by it in November 1980, found an atmosphere denser than Earth's and a surface completely hidden. And then the same trajectory that brought that encounter threw the spacecraft upward, north, out of the sheet, at an angle of roughly 35 degrees. Voyager 2 was left to carry on alone and do Uranus and Neptune, which it did, and which is why every close photograph of those 2 worlds we have came from a single spacecraft on a single afternoon each. The reason we have visited Uranus and Neptune exactly once is that Voyager 1 went to look at Titan instead and left the plane doing it. So the first object to properly climb out of the solar system's disk did so as a side effect of a decision about a moon. Nobody set out to leave the plane. It was the price of a closer look at something interesting, and they paid it. And in paying it, they accidentally put a working camera somewhere no camera had ever been. Which brings us to the most famous photograph ever taken, and to the fact that almost nobody knows why it was possible. By 1990, Voyager 1 had been climbing for 10 years. It was about 4 billion miles from home and roughly 32 degrees above the plane of the planets. It had no more planets to visit, and its cameras had nothing left to do. And Carl Sagan, who had been arguing for this for years against real institutional resistance, finally persuaded the mission to turn the spacecraft around and photograph the solar system it was leaving. There were reasons not to. Pointing the cameras back meant pointing them near the sun, which risked damaging the instruments, and the instruments were about to be switched off forever anyway to save power. So the argument was partly about whether it was worth any risk at all for a picture with no scientific value. That is the honest framing of the debate. The pictures were expected to be, and were scientifically, almost worthless. They were taken anyway. On the 14th of February 1990, Voyager 1 turned and took 60 photographs, and from them, the team assembled what is called the family portrait. It is the only image ever made of our solar system from outside it. 6 planets, each a tiny dot, in their places, photographed in a single sequence from 4 billion miles away and 32 degrees above the plane. Mercury was lost in the sun's glare. Mars was too thin a crescent to catch. Pluto was too faint. But Venus, Earth, Jupiter, Saturn, Uranus, and Neptune are all there, each a speck, a fraction of a pixel wide, and in one of those frames, caught in a shaft of sunlight scattering inside the camera optics, is a single pale dot, occupying less than 1 pixel. That is Earth. That is the pale blue dot. And it is the reason we are telling this story tonight, because here is what almost nobody puts together. That photograph exists because a spacecraft was above the plane of the solar system. If Voyager 1 had stayed in the sheet like everything else, the planets would have been strung along a line, mostly lost in the sun's glare, and there would have been no portrait to take. The most reproduced, most quoted, most emotionally significant image in the history of space exploration is a direct consequence of a trajectory chosen to look at Titan, which threw a camera 32 degrees out of the plane 10 years before anyone thought to point it back. Sagan's words about that image have been repeated so often that they have almost worn smooth, so I will not repeat them here tonight. But I want to name the thing he was actually pointing at, because it is subtler than the famous phrasing suggests. What that image shows is not that Earth is small. Everybody already knew Earth was small. What it shows is what Earth looks like from a position no human being has ever occupied or ever will, and it turns out that from up there, from a little above and a long way out, our planet is not distinguishable from a piece of dust in the optics. The photograph had to be explained. Without the caption, nobody could find us in it. That is the actual content of the most famous picture ever taken, And we have exactly one of them taken by accident by a machine that was leaving. And here is the detail that makes it ache slightly at this hour. 32 degrees is not above. It is a lean. It is the angle of a ladder against a wall. To take the picture in the textbook, looking straight down on the plane with all the orbits laid out as circles, you would need 90 degrees, and Voyager was never anywhere close and could not have been, because the only reason it got its 32 was a lucky bend around a moon. Even our one photograph from outside is a glance from the side of the room, not a view from the ceiling. The classroom diagram remains a thing no eye has seen. Voyager left the plane by accident. The next one did it on purpose, and its story is the strangest piece of orbital engineering in the history of spaceflight, and it involves flying in exactly the wrong direction for a year and a half. The mission was called Ulysses, after the Wanderer, and it was a joint European and American project with one goal that had never been attempted: not to visit a planet, to fly over the poles of the sun. Nobody had ever observed the sun from above or below. Every observation ever made of our star in the whole history of astronomy had been made from somewhere in the plane, which means from over its equator, which means we had been looking at our own star from one angle for the entirety of human history, like studying a person you have only ever seen from the waist. The problem, of course, is the 94,000 miles per hour of velocity change that no rocket can provide. So the mission designers did something that sounds like a mistake when you first hear it. Ulysses launched in October 1990 on the Space Shuttle Discovery, and it was aimed outward away from the sun in completely the wrong direction for a solar mission. It flew for 16 months, out past the asteroid belt, all the way to Jupiter, which is the last place a spacecraft studying the sun has any business going. On the 8th of February 1992, it swung in close under Jupiter, and Jupiter's gravity took hold of it and flung it, and the flinging did what no engine could ever do. It bent the trajectory almost completely out of the plane of the solar system and sent it back inward on an orbit tilted about 80 degrees, very nearly perpendicular to everything else in the solar system. Sit with the audacity of that. To look at the top of the sun, they flew away from the sun for a year and a half to the largest planet, and used it as a fulcrum to throw themselves out of the floor of the solar system entirely. There was no other way to do it. There is still no other way to do it. It remains, more than 30 years later, the only spacecraft that has ever properly flown over the poles of our star. And then it did something quietly heroic, which is that it kept going for 18 years. The nominal mission was 5. Ulysses ended up making 3 complete passes over each pole, timed so that the passes fell at different points in the sun's 11-year activity cycle, once near quiet minimum and once near violent maximum, so that the comparison could be made. It was finally shut down on the 30th of June 2009 after 18 years and 8 months, not because anything broke, but because its plutonium power source had faded to the point where the fuel lines were in danger of freezing solid. So what did it see? when it finally got above. The headline discovery is the sort of thing that sounds modest and is actually foundational. Before Ulysses, the solar wind, the stream of charged particles the sun pours out constantly in every direction, was understood almost entirely from measurements taken in the plane. And in the plane, it is messy, gusty, variable, a turbulent stream of fast and slow patches sliding past each other. Ulysses climbed above that and found something quite different. Over the poles at high latitudes, the solar wind is not messy at all. It is fast, it is remarkably steady, and it blows uniformly at roughly double the speed of the slow wind found near the equator. The sun, it turned out, has two winds. A fast, steady one from the poles, and a slow, choppy one from the equatorial belt, and everything humanity had measured for decades had been the slow one, because we were sitting in the slow one, because we live in the plane. That is the kind of discovery this direction offers, not a new object. A correction to something we already thought we knew, produced entirely by looking from somewhere else. Every solar measurement before 1992 came from one viewpoint, and the moment we got a second viewpoint, the picture changed. Ulysses found other things too. It measured the sun's magnetic field over the poles and found that its strength did not vary with latitude the way the models expected, which told theorists something important about how the field spreads out into the solar system. It flew through the tails of comets unexpectedly twice, including a crossing of the tail of comet Hyakutake so far from the comet itself that it revealed those tails to be far longer than anyone had believed. It measured interstellar dust drifting into the solar system from outside, which is far easier to detect when you are not sitting in the thick of our own dust. And on its later passes, near solar maximum, it found the neat 2 wind structure had broken down entirely, the fast polar wind giving way to a chaotic mixture at all latitudes, revealing that the tidy picture from the quiet years was only half a cycle's worth of truth. None of that could have been learned from the plane. All of it came from the one machine willing to spend a year and a half flying the wrong way. Let this be tonight's long stillness then, and let it be quiet. Come up with it. Ride along on that tilted orbit above the sheet and look around. The first thing you would notice is what is missing. From up here, there is no band of light across the sky. Down in the plane, the zodiacal light, the faint glow of sunlit dust spread along the ecliptic, is a permanent feature, and the planets are strung along it like beads on a wire. From up here, the dust is below you, seen as a thin, luminous sheet, and above you, there is nothing but stars. No band, no line. The sky is simply open in every direction, which is a thing it has never been for any observer on Earth. Below you, the solar system is laid out, not as a diagram, because at any real distance the planets are points and the orbits are invisible, but as an arrangement. The sun is the obvious center, and near it, if you knew where to look and had a good enough eye, the inner planets would be in their places, not strung out in a line as they always appear from home, but spread apart at their true angular separations. In a plane, you are finally seeing at an angle rather than edge on. It is the same set of objects you have known your whole life, arranged in a way no human being has ever seen them arranged. And the sun itself is the strangest part. From above the pole, you are looking down at a region of our star that no ground telescope can ever properly observe. The sun's poles are where its magnetic field reverses every 11 years, where the field lines open out into the solar system, where the fast wind comes from. It is the engine room of the whole magnetic cycle, and from Earth we can only ever glimpse it, obliquely, foreshortened, at a hopeless angle, the way you would try to study the top of someone's head from across a table. It is very quiet up here. Nothing is passing, no dust to speak of, no traffic of comets and asteroids, because they are all down in the sheet. Just the fast, steady wind blowing past at 1.5 million miles per hour in perfect silence, and an unobstructed view in every direction, and beneath you the entire arrangement of everything anyone has ever known, turning slowly, all of it in one flat layer, with a great deal of nothing above and below. And then, for a long time, nothing. Ulysses fell silent in 2009, and for over a decade there was nobody above the plane at all, and the poles of the sun went back to being a place we had visited once and could not return to. Which brings us to the third machine, and this one is happening right now while you are lying there, and it took a completely different approach to the same impossible problem. The mission is called Solar Orbiter, a European spacecraft with American participation, and it launched in February of 2020. It faced the same wall as everyone else. No rocket can buy an inclined orbit. Ulysses had solved it by going to Jupiter, but Jupiter is an expensive detour. It takes years, and it throws you so far from the sun that you can only make close observations occasionally. Solar Orbiter wanted something different. It wanted to get above the plane and stay close to the sun, to look down at the poles from near enough to see detail. So it is climbing a staircase, and the steps are Venus. The technique is patient in a way that is almost hard to believe. Solar Orbiter flies inward, passes Venus, and takes a small amount of orbital tilt from the encounter. Then it flies around the Sun on its slightly tilted orbit and comes back to Venus, arriving in resonance, meaning the timings are arranged so that Venus is always waiting exactly where it needs to be. Another pass, another few degrees, then again and again. Each Venus encounter is a step, and the spacecraft is walking itself up out of the plane a fraction at a time, using nothing but the repeated gravity of a planet that has no idea it is being used as a staircase. It has been doing this for years. And on the 18th of February 2025, it made the pass that mattered, coming within about 380 kilometers of Venus, close enough that a mistake would have been catastrophic, and that encounter lifted its orbit from about 7.5 degrees of tilt to around 17. 17 degrees does not sound like much, and against the 90 you would want, it is not. But it was enough. In March of 2025, from that new vantage point, Solar Orbiter began returning the first direct views of the Sun's polar regions ever obtained by any spacecraft with modern imaging instruments. Think about that date for a moment, because it is astonishingly recent. Human beings have been watching the Sun for the entire history of our species. We built stone monuments to track it. We predicted its eclipses thousands of years ago, and the first time anyone properly saw the top of it was last year. And the mission is not finished climbing. The plan calls for continued Venus encounters through the extended mission, raising the inclination further, with the goal of reaching something like 33 degrees relative to the Sun's equator by around 2029. Each additional step buys a better view of the pole and a better look at what is genuinely one of the outstanding problems in solar physics, which is how the Sun's magnetic field reverses itself every 11 years. That reversal appears to begin at the poles. We have never been able to watch it happen from a sensible angle. Over the next several years, for the first time, we will. There is something quietly moving about the difference between the two approaches. Ulysses solved the problem with a single enormous act, one violent encounter with the largest planet, a great leap out of the floor of the solar system in one motion at the cost of never being able to get close to the Sun. Solar Orbiter is solving it by patience, a few degrees at a time, going round and asking Venus for a small favor on each pass over the better part of a decade. Both are correct. Both are, in their way, the same trick that every spacecraft that has ever left the plane has used, which is that we cannot afford to climb, so we ask a planet to lift us. And that, in total, is the list. Voyager 1, which left by accident on its way past a moon. Ulysses, which went to Jupiter to look at the Sun. Solar Orbiter, which is climbing a Venus staircase right now. There are a few honorable mentions: spacecraft on modestly inclined orbits, and Voyager 2 also left the plane in the opposite direction, downward, after Neptune bent its path south. But as a complete accounting of humanity getting meaningfully out of the sheet in 70 years of spaceflight, that is essentially it. Fewer machines than you have fingers on one hand. Which brings us back to the photograph that does not exist, and to why it still does not, and probably will not, for a long time. Because you might reasonably ask, now that we understand the difficulty, why nobody has simply flown a camera to a high angle and taken the picture? And the answer is a hard one. It has no scientific value. Not none exactly, but very little. The positions of the planets are known to fantastic precision already, computed rather than photographed, and a portrait from above would teach us essentially nothing. We do not already know to more decimal places than the photograph could resolve. The family portrait was itself nearly cancelled for exactly this reason. And it was taken only because a spacecraft happened to already be up there with nothing else to do and an advocate who would not let it go. So the picture on the classroom wall stays a drawing, not because we could not manage it, but because there is no mission whose science case is a photograph, and there is something quite tender in that, and slightly sad and very human. We will build a telescope to photograph the atmosphere of a planet 40 light years away, and we will spend billions doing it, and we have never taken a family photograph of the house we grew up in because nobody could justify the fuel. There is a companion to the Voyager 1 story that completes it beautifully, and it happened 9 years later at the other end of the solar system. Voyager 2, left behind to carry on the grand tour alone, went to Uranus in 1986, and then to Neptune in 1989, and at Neptune, the mission faced its own version of the same choice. There was a moon worth seeing, and the moon was Triton, and getting close to it required bending the trajectory. So the encounter was flown low over Neptune's North Pole, using the planet's gravity to swing the spacecraft down toward Triton, and the price of that geometry was that Voyager 2 was thrown out of the plane of the solar system, downward, south, the mirror image of what happened to its twin. So the two Voyagers are now leaving the solar system in opposite vertical directions, one climbing north above the plane, one descending south below it, both because each of them was aimed at an interesting moon at the end of its planetary tour. Neither departure was planned as a plane change, both with the cost of a closer look at something with an atmosphere. I find that a lovely accident of history. Humanity's two most distant machines are spreading apart in the one dimension we cannot travel in purely because of decisions about Titan and Triton made by different teams a decade apart. And it turned out to matter enormously, for a reason nobody anticipated when those trajectories were chosen. Because the sun is not sitting still, it is moving through the interstellar medium, the thin gas between the stars, at something like 50,000 miles per hour, and as it moves it inflates a vast bubble in that gas with its own outflowing wind. That bubble is called the heliosphere, and it is the true outer boundary of the sun's domain, the place where the solar wind finally slows and stops against the pressure of interstellar space. And because the sun is moving, the bubble is not a sphere. It is shaped, compressed on the leading side, drawn out behind, and quite possibly asymmetric top to bottom as well, which means that where you cross the boundary matters. And by pure chance, we ended up with two probes crossing it in two different places, one above the plane and one below. Voyager 1 crossed into interstellar space in 2012. Voyager 2 crossed in 2018, 6 years later, and at a noticeably different distance from the Sun. If the heliosphere were a simple sphere, they should have crossed at the same distance. They did not, and the difference is real data about the shape of the bubble we live in. Two spacecraft, sent in different vertical directions for reasons having nothing to do with any of this, gave us the only two measurements of that boundary humanity has ever made from two different places on it. That is the third time tonight that leaving the plane produced something valuable that nobody set out to get. The family portrait came from a trajectory chosen for Titan. The comparison of the heliosphere's shape came from trajectories chosen for Titan and Triton. Ulysses is the only one of the three that went up on purpose, and even it had to pretend to be going to Jupiter to do it. There is a lesson in that about exploration generally, and it is not a tidy one. The valuable things have mostly come from being somewhere unusual with working instruments, rather than from going somewhere unusual in order to get them. You cannot plan the pale blue dot. You can only build machines that last, send them somewhere interesting, and then, when they end up somewhere nobody expected, be the sort of organization that remembers to turn the camera around. And yet, we have the drawing. That is the part worth pausing on, because it is easy to hear tonight's story as a story about a limitation, and there is something far more impressive hiding inside it. We have never seen the solar system from above. We know exactly what it looks like from above anyway. Every one of those classroom diagrams, for all that they are illustrations rather than photographs, is correct. The positions are right. The distances are right. The orbital shapes and tilts and periods are right to a precision that would let you land a spacecraft on a specific rock 1 billion miles away after a 9-year flight, which we have done. We drew an accurate map of a place from a vantage point nobody has ever occupied, using nothing but observations taken from inside it, at a bad angle, through an atmosphere. How? By watching things move and doing arithmetic for 400 years. The whole enterprise starts with a genuinely maddening problem, which is that everything you see in the sky is moving, and you are moving too, and you cannot feel your own motion, and you have no depth perception at these distances whatsoever. Every object in the sky appears painted on the same imaginary dome. From that, with no way to step outside, human beings worked out the three-dimensional arrangement of the entire solar system. It is one of the great intellectual achievements of our species, and it took an unreasonable amount of patience. The pivotal figure is Johannes Kepler, working in the early 1600s with the observations of Tycho Brahe, who had spent decades measuring planetary positions to a precision nobody had matched, all by eye, before the telescope. Kepler spent years, by his own account, something like 40 attempts, trying to fit the motion of Mars to a circle and failing by a small, stubborn margin that would not go away. Anyone else would have called it observational error. He trusted the data more than he trusted the assumption, which is the whole of science in one sentence, and eventually tried an ellipse, and the discrepancy vanished. And from those laws, and later from Newton's gravity, a remarkable thing became possible. You could compute the true shape of an orbit, its size, its tilt, its orientation, from nothing but the changing angle at which you saw the object from Earth over time. You never needed to leave. The information about the third dimension was hidden in the way things moved against the sky, and once you knew what mathematics to apply, it came out. The map assembled itself from the motion. That is how every number in tonight's story was obtained. Nobody measured the tilt of Mercury's orbit by flying above it and looking. They measured where it appeared night after night for years and solved for the geometry that would produce that pattern. The invariable plane, that permanent midline of the whole system, was not observed. It was calculated, by adding up the angular momentum of every significant body in the solar system, which required knowing all their masses and orbits, which required centuries of work by hundreds of people who mostly never met. So, there is a real distinction hiding in tonight's subject, and it is worth naming clearly, because it is the difference between two kinds of knowing. We know the solar system from above in the sense that we can compute it, predict it, and navigate it with total confidence. We do not know it from above in the sense of having looked. And those are genuinely different, and the difference is not scientific, but something closer to emotional. Nobody has stood at the window. The same distinction shows up in a place you know well. We have known the mass, distance, orbit, and composition of the moon for a very long time. We had every number. And then, in 1968, the crew of Apollo 8 came around the far side and saw the Earth rise over the lunar horizon and photographed it. And that photograph changed a great many things that no amount of correct numbers had changed. The data did not tell people what the picture told them. That is the gap we are talking about tonight. And for the solar system as a whole, the picture has never been taken. There is one more thing our arithmetic gives us that our eyes never could, and I find it genuinely lovely. Because we can compute the arrangement, we can also compute what it looked like at any moment in the past and what it will look like at any moment in the future. We know where every planet was on the day you were born. We know where they were when the pyramids were built. We know, within the limits of long-term chaos, where they will be 100,000 years from now. We have a map not just of a place we have never seen, but of that place across time in both directions, running smoothly. So the missing photograph is not a hole in our understanding. It is a hole in our experience, and those are worth different things, but they are both worth something, which is exactly why a mission with no scientific value was worth arguing for in 1990, and why the picture that came back is the one people actually remember. There is a practical consequence of all this that shapes everything humanity does in space every single day, and it is invisible unless you go looking for it. The plane is a highway, and essentially all of our traffic uses it. Consider how a mission to another planet is actually planned. You do not point at your destination and fire because your destination is moving and so are you. Instead, you look for a transfer orbit, an ellipse around the Sun that touches Earth's orbit at one end and the target's orbit at the other, and you time your departure so that the target arrives at the meeting point at the same moment you do. That is the cheapest way to get anywhere. And it works beautifully, and it depends completely on both worlds being in the same plane. If Mars orbited at a steep angle to Earth, every mission would need an expensive plane change on top of everything else, and our exploration of the solar system would have been a fraction of what it has been. This is why launch windows exist, and why they are so unforgiving. A window to Mars opens roughly every 26 months because that is how long it takes for the two planets to return to the right relative positions. Miss it, and you wait more than 2 years, not because anything is broken, but because the geometry has moved on. Every mission to every planet has been governed by this. Every image you have seen of another world exists because someone caught a window. And the flatness makes something else possible that we lean on constantly, which is the gravity assist we discussed earlier. Those trajectories are the reason we have seen the outer solar system at all, and they only work because the planets are all in roughly the same plane, and therefore available to be strung together. The grand tour that the Voyagers flew was a chain of encounters, each one setting up the next, and you can only chain encounters if the objects are lined up in one layer. In a solar system with randomly tilted orbits, the grand tour would have been geometrically impossible, and Uranus and Neptune would still be unvisited, and possibly always would be. So, the sheet is not only where everything is, it is what makes everything reachable. The same flatness that traps us is what has allowed a species with modest chemical rockets to touch every planet in its system. If the solar system had been a swarm rather than a disk, we would have reached Mars and perhaps Venus and then stopped, because every further target would have cost a plane change we could not pay for. There is a nice illustration of this in the way spacecraft trajectories look when you plot them. Draw the path of any interplanetary mission on a diagram of the solar system seen from above, and you get an elegant curve, a spiral arc from one orbit to another, and it makes sense immediately. Now draw the same trajectory in the vertical dimension, viewed edge-on, and you get an almost perfectly flat line with a barely perceptible wiggle. In 70 years, essentially everything humanity has flown between planets has stayed within a couple of degrees of a single sheet. Our entire history in deep space, plotted from the side, is a straight line. And that is why the vertical direction is not merely unvisited, but almost unconsidered. There is no reason to go up. There is nothing up there to visit, no target, no destination, no gravity, well to fall into. Space agencies fund missions to places, and up is not a place. It is a direction with a view, and a view has never been enough to justify the fuel, with one glorious exception, which we have already discussed, and which had to be argued for by a man who kept refusing to let it drop. Which means the emptiness above us is not just unexplored. It is structurally unexplorable under the way we currently decide what to explore. Not because it is hard, though it is, but because our entire framework for choosing where to send things is built around destinations, and the space above the plane offers none. It offers only perspective. And nobody has yet worked out how to write a mission proposal whose deliverable is perspective. Now let us take the census of the vertical properly, because I told you earlier that there is almost nothing above and below the plane, and almost is doing some work in that sentence. There are things up there. They are simply not the things you would expect, and each of them tells you something about the history of the system. Start with the comets, because comets were the first clue that the solar system is not entirely flat, and they were noticed centuries before anyone could explain them. Every planet moves in the plane, in the same direction, in a near circle. Comets do nothing of the sort. They arrive from every direction, from above the plane and below it, some going the wrong way round the Sun entirely, on orbits so stretched that they spend nearly all their time in the far dark, and only a few months of each enormous year anywhere near the light. For a long time this was simply a fact about comets, an oddity. It is now one of the strongest pieces of evidence we have about the shape of the outer solar system. Because if comets came from a disk, they would arrive in the plane. They do not. The long-period comets, the ones with orbits of thousands or millions of years, arrive from all over the sky, evenly distributed, with no preferred direction whatsoever. The only structure that produces that pattern is a sphere, and that is the reasoning that led astronomers in the middle of the 20th century to conclude that the solar system is surrounded, far out beyond everything, by a vast spherical shell of icy bodies. The Oort cloud. Nobody has ever seen it. Its existence is inferred almost entirely from the directions comets come from. So the shape of our home is stranger than the classroom diagram suggests. There is a flat disk of planets, immensely thin in the middle, and then at distances thousands of times greater, there is a spherical halo wrapped around the whole thing in every direction, including straight up and straight down. Our solar system is a dinner plate inside a beach ball. The plate is where everything we have ever visited lives. The ball contains, by number, almost all of the objects that belong to the Sun. Between the two, there is a transitional population that is genuinely tilted, and it is worth a moment. The scattered disk, which we met on another night, is full of objects on steeply inclined orbits thrown there by Neptune's ancient migration. Some ride at 30 degrees, some far higher, and beyond even them, out among the far wanderers, are objects like Sedna on orbits so detached and strange that nobody can yet explain how they got there. If you want to find something in our own solar system that is genuinely, permanently above the plane, those are your candidates, and we know almost nothing about any of them. Then there is the dust, and here is a detail I like a great deal. The inner solar system contains a faint haze of dust, ground off asteroids and shed by comets, and it lies in the plane like everything else. On a very dark night, at the right time of year, an hour or so before dawn or after dusk, you can see it with your naked eye as a faint, triangular glow rising from the horizon along the ecliptic. It is called the zodiacal light, and most people who see it assume it is light pollution or the beginnings of dawn. It is sunlight reflecting off the flattened dust of our own solar system, seen edge-on from inside. It is possibly the only structure of the solar system as a structure that is directly visible to the unaided human eye. And it is visible precisely because we are in the plane looking along it, so the dust piles up along our line of sight. From above, it would be a faint disk you could barely see at all. And finally, the visitors. In recent years, astronomers have detected the first objects to pass through our solar system from interstellar space, wanderers ejected from other star systems long ago and drifting between the stars until they happen to fall past our Sun. The first, was found in 2017, and what marked them out immediately as foreign was not their composition or their appearance. It was their trajectories. They arrived on paths steeply inclined to the plane, moving too fast to be bound to the sun, coming in from above and leaving through the bottom. Anything native to the solar system inherits the plane. Anything that ignores the plane entirely is announcing that it came from somewhere else, which gives you a neat way to hold the whole picture. In our solar system, the flatness is the family resemblance. Everything that formed here inherited the spin of the original cloud and lives in the sheet. The further from the sheet an object's orbit is, the stranger its history must be, and at the extreme, if it is not in the plane at all and never was, it is not ours. The direction we never look, in other words, is the direction that everything foreign comes from. Not because anything is aiming at us from up there, just because the plane is what we inherited, and anything that did not inherit it is by definition from elsewhere. And now I want to point out how much of your ordinary experience of the sky is a direct consequence of living inside the plane. Because once you see it, you cannot unsee it. And most of it is stuff you have known since childhood without knowing why. Start with eclipses, which are the most spectacular thing the sky does, and which happen for a reason that is entirely about flatness. The moon orbits Earth roughly, though not exactly, in the same plane that Earth orbits the Sun. It is tilted by about 5 degrees, which is small but not nothing. If the moon's orbit were perfectly aligned with the ecliptic, we would get a solar eclipse every single new moon, and a lunar eclipse every full moon twice a month forever, and eclipses would be about as remarkable as a Tuesday. If instead the moon orbited at a steep angle, we would get almost none at all. Because the tilt is 5 degrees, the alignment only works when the geometry lines up just so, which happens a handful of times a year, in seasons, at the points where the moon's tilted orbit crosses the ecliptic. Those crossing points even have a name. The nodes and the entire ancient science of eclipse prediction, going back thousands of years to Babylonian astronomers, is the science of tracking where those nodes are. Every eclipse in human history has happened because our satellite very nearly, but not quite, shares our plane. Then there is the zodiac, which is not astronomy, but which came from astronomy, and which is a direct artifact of the plane. The sun, over the course of a year, appears to travel all the way around the sky along the ecliptic. The constellations it passes through, 12 of them by ancient convention, are the zodiac. They are not special stars. They are simply whichever stars happen to lie along the line that our own orbital plane projects onto the sky. And the planets appear in those same constellations for the same reason. When ancient astronomers noticed that the wandering stars all kept to one narrow road through the heavens and built enormous systems of meaning on top of that observation, what they had actually detected, without any way of knowing it, was the flatness of the solar system. The zodiac is the plane, misread. And then the strangest of the ancient puzzles, which is retrograde motion. Watch Mars carefully over months and it moves steadily eastward against the stars, then slows, stops, reverses, travels backward for weeks, stops again, and resumes going forward. Every planet does some version of this. For 2,000 years, this was the central problem of astronomy, and the geocentric model required an elaborate apparatus of circles riding on circles to reproduce it. The true explanation is simply that we are on a moving platform, overtaking or being overtaken by another moving platform. And the apparent reversal is a parallax effect of our own motion, like a car you pass on a motorway appearing to slide backward. But notice that the effect is as clean and dramatic as it is precisely because both platforms are in the same plane. If the planets orbited at wild angles to each other, their apparent paths would be complicated loops all over the sky rather than a neat back and forth along one line. And it is not at all obvious that anyone would ever have untangled it. So, the shape of our home determined the shape of our confusion, and therefore the shape of the science that resolved it. Copernicus, Kepler, Galileo and Newton were all, in a sense, working on a problem that exists in the specific form it does, because we live inside a flat disk and see it edge on. An intelligent species on a planet in a system with badly misaligned orbits would have had a completely different astronomical history, harder in some ways and possibly easier in others, and they would certainly never have invented a zodiac. One more, and it is my favorite. The reason we can find new planets around other stars by watching them dim, the transit method that has given us thousands of worlds, works only because planetary systems are flat. A planet must pass directly between us and its star for a transit to happen. And if a system's planets were scattered at random angles, the chance of catching even one would be tiny, and the chance of catching several around the same star would be effectively zero. But because systems are disks, if you catch one transiting planet, you have found the system's plane, and you know that any other planets are very likely in that same plane, and therefore also likely to transit. That is why so many multi-planet systems have been discovered. Flatness is why the census works. The disk shapes what we can see, what we could figure out, and what we can find elsewhere. It gave us eclipses and the zodiac and retrograde motion and the transit method, and it is the reason nobody has ever seen it. And there is one more motion to account for, which changes the picture of the flat sheet in a way I find genuinely delightful, because it means the plane is not sitting still either. The whole solar system is moving. Not just the planets around the sun, but the sun itself, carrying everything with it, traveling through the galaxy. It is going at roughly 500,000 miles per hour around the galactic center, a lap that takes something like 230 million years. So the last time the sun was in this part of its orbit, the first dinosaurs were appearing. And on top of that great circuit, the sun is also drifting relative to the stars immediately around it, heading toward a point in the constellation Hercules that astronomers call the solar apex. So the flat sheet is not a stationary disk. It is a disk in transit, moving broadly edge-on through the gas between the stars, which is why the heliosphere has a compressed leading side and a trailing tail, and why it matters where the Voyagers crossed it. But here is the part that reframes tonight's geometry. The direction the solar system is traveling has nothing to do with the direction of up. The plane is tilted about 60 degrees to the plane of the galaxy, and the sun's motion is its own separate thing again. So, as the whole arrangement moves, it is not flying face-on like a frisbee thrown flat, and it is not flying edge-on like a coin rolling. It is going at an angle, tilted, carrying its sheet of planets through the galaxy the way you might carry a dinner plate at a slant while walking across a room. Which means the planets are not really tracing circles at all. Add the sun's motion through the galaxy to their orbits around the sun, and every planet's true path through space is a helix, a long spiral drawn out behind it, never once returning to where it has been. Earth has completed 4.5 billion laps of the sun and has never retraced a single mile of its actual path through the galaxy. Every orbit you have ever completed, all 40 or 50 or 70 of them, has been a fresh loop of a corkscrew drawn through space that no part of this planet had ever occupied before. I want to be careful here because this idea gets exaggerated online quite badly, usually with a dramatic animation claiming that the planets trail behind the sun like a vortex, which is wrong, and which some astronomers spend a genuinely irritating amount of time correcting. The planets do not lag behind. The orbital plane's orientation stays fixed as the sun travels. It does not get dragged into a cone, and from the sun's own frame, everything is doing exactly the neat, flat circles we have described all night. The helix is real, but it is a fact about which reference frame you choose, not a hidden truth the diagrams are concealing from you. Still, with that caveat honestly stated, it is worth holding once before we close. The flat sheet we have spent tonight inside is moving, tilted, through a much larger flat sheet at 500,000 miles per hour, and has been for the entire history of life on Earth. The floor of the solar system is not a floor, it is more like the deck of a ship, level with respect to itself, in constant motion with respect to everything else, and carrying every one of us at a speed that makes our fastest spacecraft look stationary. You are not lying still. You are on a spinning planet, on a tilted plate, being carried through a galaxy, and the only reason any of it feels like a solid floor is that everything nearby is coming along at the same speed. And now the turn I have been saving, because everything we have said tonight about the solar system is true at a vastly larger scale of the galaxy, and we are sitting inside both of them at once. The Milky Way is a disk, not loosely, a genuine flattened disk produced by exactly the same physics we described earlier, a spinning cloud collapsing and flattening, only this time with a few 100 billion stars in it, and it is proportionally far thinner than most people picture. The galaxy is roughly 100,000 light-years across, and the thin disk where most of the young stars and essentially all of the gas and dust live is perhaps 1,000 light-years thick. Take a ratio of 100 to 1. and build a model. If the Milky Way were the width of a large city, its star-forming layer would be about the thickness of a sheet of paper laid across it, and we are in it, not near it, not above it. The sun sits inside the thin disk, close to the midplane, and it bobs gently up and down through it as it orbits the galactic center, crossing the midline every few tens of millions of years like a horse on a very slow carousel. Which means everything we said about the solar system applies again, one level up. We live inside a sheet. We see that sheet edge on, and it appears to us as a band. You have seen it. On a genuinely dark night, away from any town, there is a faint river of light arching across the sky, and it is not a cloud and not a nebula. It is the combined glow of hundreds of billions of stars in the disk we are inside, seen edge on from within. That is why the Milky Way looks like a band rather than a spiral. We are not looking at our galaxy. We are looking along it. And exactly as with the solar system, we cannot get out. This time, the impossibility is not a matter of fuel. It is absolute. To rise far enough above the galactic disk to photograph the Milky Way from outside would mean traveling many thousands of light years perpendicular to it, which at any speed we could ever conceive is a journey of tens of millions of years. Every picture you have ever seen of our galaxy, seen face on with its spiral arms laid out beautifully, is a painting. Every single one. It is a reconstruction, assembled from measurements of star positions and motions and gas velocities drawn by artists working from data, exactly as the solar system diagram is. We have never photographed our own galaxy, and we never will. So the missing photograph is not a peculiarity of the solar system. It is our permanent condition. We are inside a disk, and we cannot step outside either of them. And every image we possess of our own home at either scale is an inference dressed up as a picture. But here is the part that lifts it, and it is the same lift as tonight's whole story, because the astronomers did the same thing at galactic scale that Kepler did at solar scale. They could not step out, so they measured motion instead. A European spacecraft called Gaia spent years measuring the positions and movements of well over 1 billion stars with fantastic precision, building a three-dimensional map of our galactic neighborhood from the inside. And from that map, we now know the structure of the Milky Way's disk, the shapes of its arms, the warp along its outer edge, and the fossil traces of ancient galaxies it swallowed billions of years ago, all from inside, all from watching things move, all without ever once seeing the thing we were mapping. And there is a beautiful practical consequence of living in the galactic disk that ties directly back to tonight. Because the disk is full of dust, and dust blocks light, looking along the plane of the Milky Way means looking through the smoke. The galactic center is only 26,000 light-years away, which is nothing compared to the depths we routinely observe, and we cannot see it in visible light at all. It is completely hidden behind intervening dust. But look perpendicular to the disk, straight up out of the galaxy, and the dust thins out in a few hundred light years, and then there is nothing in the way at all the way to the edge of the observable universe. So when astronomers want to look as deep into the universe as possible, they point away from the plane of our galaxy. The famous deep field images, those long exposures that reveal thousands of galaxies in a patch of apparently empty sky, are aimed well away from the Milky Way's band, out through the thin part, because that is where the windows are. The direction we cannot travel is the direction we can see furthest in. Up, out of the plane, is simultaneously the most inaccessible direction in our lives and the clearest one. I find that a very satisfying place to arrive at, this far into the night. The same geometry that traps us is the geometry that gives us our view. We are stuck in two sheets, unable to rise out of either. And the thinness of those sheets is precisely why, when we look in the one direction we can never go, we can see almost all the way to the beginning. Before we turn for home, one more scale of flatness, going the other way, downward into the small, because the pattern repeats there too, and it makes the whole thing feel less like a fact about our solar system, and more like a habit of the universe. Look at Jupiter. It has 90-odd known moons, and the 4 large ones, the Galilean moons that Galileo saw through his first telescope, orbit in a neat, flat plane around Jupiter's equator in the same direction, in near circles, in resonance with one another. It is a miniature solar system, and it is flat for exactly the same reason the big one is. Jupiter formed from its own local collapsing, spinning cloud, and that cloud flattened into a disk, and the moons condensed out of the disk. Saturn is the same. Uranus is the same, tipped sideways along with its planet, its moons faithfully orbiting the equator of a world lying on its side, which is itself rather good evidence that whatever knocked Uranus over did it early, before the moons formed. And then Saturn's rings, which are the purest example in the solar system of the physics we described at the beginning, running in front of your eyes at a scale you can photograph in an evening. The rings are a couple of 100,000 miles across, and in most places only tens of meters thick. Take the ratio. If you scaled the ring system to the size of a football pitch, it would be very much thinner than a sheet of paper, thinner than a human hair. It is the flattest large structure anyone has ever measured, and it is flat because of collisions. Any particle on a tilted orbit repeatedly crosses the main ring plane, and every crossing means collisions with particles that are in the plane, and every collision cancels a little of the vertical motion, and after enough crossings the tilt is gone. Anything that will not flatten is ejected or falls in. What remains necessarily is a sheet. That is the same process that flattened the solar system, only running faster because the rings are dense and collisions are frequent. Saturn shows you the mechanism working in visible form. The solar system did that 4.5 billion years ago and then stopped, and you cannot watch it happen. Saturn is still doing it now. So the nesting runs the whole way down and the whole way up, rings around a planet, flat. Moons around a planet, flat. Planets around a star, flat. Stars around a galactic center, flat. Gas spiraling into a black hole, flat. And in every one of those cases, the flatness has the same cause, a spinning cloud that could collapse freely along its axis and not across it. And in every one of those cases, the flatness produces the same consequence for anyone living inside it, which is that the interesting direction, the direction with a view, is the one direction nothing is arranged to take you. There is a version of this that is genuinely strange to think about at this hour, so let me offer it and then let it go. Every structure we have just listed is flat because it is spinning, and each one is embedded in the next at a different angle. Saturn's rings are tilted with respect to Saturn's orbit. Saturn's orbit is tilted with respect to the invariable plane. The invariable plane is tilted with respect to the Sun's equator. The whole solar system is tilted at about 60 degrees to the plane of the Milky Way, which is why the band of the galaxy crosses our sky at a steep angle to the ecliptic rather than lying along it. The Milky Way's own disk is tilted with respect to the plane of our local group of galaxies, layers of flatness, each one nested inside a larger one, each at its own angle, none of them agreeing, like a stack of plates dropped in slow motion and frozen mid-fall. That is the actual architecture of where you live, and no diagram has ever really shown it, because to draw it, you would have to be outside all of them at once, which is a place that does not exist. Let us come back down to our own star and go and stand where Solar Orbiter is standing, because the Sun's poles deserve their own hour, and they are genuinely one of the last unexplored places that is close enough to matter. Here is why the top of the Sun is interesting, rather than merely unvisited. Our star has a magnetic field generated by the churning of electrically conducting plasma in its outer layers, and that field does something no other object in the solar system does. Every 11 years or so, it reverses. North becomes south. The whole magnetic structure of the Sun turns itself inside out, and then, 11 years later, does it again. This is not a subtle effect. It drives the sunspot cycle. It drives solar flares and the great eruptions of plasma that occasionally cause auroras and disturb power grids on Earth, and the entire rhythm of space weather across the solar system is set by it. And nobody knows exactly how it works. There are good models. The general picture involves the Sun's differential rotation. The fact that its equator turns faster than its higher latitudes, winding the magnetic field up like a twisted rubber band until it becomes unstable, with material flows carrying magnetic remnants poleward, where they cancel the existing polar field and eventually rebuild it in the opposite direction. That is the story, and the crucial part of it, the part where the reversal actually happens, occurs at the poles, which we could not see. From Earth, and from every spacecraft except Ulysses, the Sun's poles are viewed at a grazing angle, foreshortened almost to invisibility, with the near side of the pole hidden by the curve of the star. Trying to study the magnetic behavior of the polar regions from the plane is like trying to read the expression on someone's face while standing behind them. All the theory about how the solar cycle works has therefore rested on measurements taken almost entirely of the middle latitudes, extrapolated upward. Ulysses could measure the wind and the field strength at high latitude, and it did, and that was invaluable. But Ulysses carried no cameras of the kind that could image the sun's disk in detail, and its orbit took it far away, out past the asteroid belt, so it was watching from a great distance. Solar Orbiter is the first spacecraft to combine both things, a tilted orbit and a close approach with modern imaging instruments, and that combination is why the pictures it started returning last year matter. So let this be tonight's second stillness. Ride with it at 17 degrees above the plane, closer to the sun than Mercury ever gets, and look down. The star fills a huge part of the view, several times wider than the sun appears from Earth, and it is not the flat white disk you know from a glance on a summer afternoon. Seen in the wavelengths these instruments use, it is a churning, granular, restless surface, covered in convection cells the size of countries, each one a column of rising plasma that breaks the surface, spreads, cools, and sinks, the whole face of the star bubbling like a pot. And now look toward the pole, which is the thing nobody had ever properly done. Down there, at high latitude, the surface changes character. The mottled magnetic activity of the middle latitudes gives way to something the observations have found to be far more complicated than the neat models predicted. Instead of a clean, single magnetic polarity capping the pole, as a simple bar magnet picture would suggest, the region shows a patchwork north and south polarities present together, which is exactly what you might expect to see at a moment when the field is in the middle of flipping over. The mission caught the pole during the reversal itself, which is either extraordinary luck or good scheduling, depending on how generous you feel toward mission planners. Above the polar region, the corona opens out. Here, the magnetic field lines that in the middle latitudes loop back down to the surface instead stream outward, unclosed, straight into the solar system. These open regions are called coronal holes, and they appear dark in the right wavelengths precisely because the hot material is escaping rather than being held. And it is out of those open field lines that the fast solar wind blows, the wind Ulysses measured 30 years earlier without being able to see where it came from. Sit above the pole, and you are looking directly down the barrel of the thing that fills the entire solar system with charged particles, the wind that shapes every planet's magnetosphere, that pushes comet tails, that carves the enormous bubble our whole system lives inside. It is worth appreciating how long we waited for this. Every civilization that has ever existed watched the sun. We have measurements of sunspots going back over 4 centuries. We have understood nuclear fusion for the better part of 100 years. And the first proper look at the top of it happened while you were going about an ordinary year of your life from a spacecraft that had spent 5 years climbing a staircase made of a planet. There are more steps to climb. 33 degrees is the target several years out. That is still not above. It is still a lean, not a view from the ceiling, and the true overhead perspective on our own star remains, like the family portrait, a thing nobody has managed. But it is the closest anyone has come, and it is happening now, and by the time this mission ends we will have watched a magnetic reversal from a place no one had ever stood. So will anyone ever take the picture? Let us give the question a serious answer, because there are real proposals, and the honest assessment is more interesting than a simple yes or no. The first thing to say is that the difficulty we described at the start is permanent under chemical propulsion. No arrangement of the rockets we currently fly gets a useful payload to a steeply inclined solar orbit directly. That is not a funding problem. It is arithmetic, and the arithmetic does not soften. So every serious concept works around it in one of three ways. The first is the one we have already seen used twice, which is to borrow from a planet. Jupiter can throw you almost anywhere, including out of the plane, and it remains the only single maneuver that gets you to a genuinely high inclination in one step. The cost is that Jupiter is 5 times further from the Sun than we are. So anything Jupiter throws ends up on an enormous slow orbit and cannot linger near the Sun. Venus can only give small increments, which is why Solar Orbiter has to climb for a decade. There is no planet in a convenient place to do both. The second approach is to stop using chemical rockets. Solar electric propulsion, ion engines produce a tiny thrust continuously for years rather than an enormous thrust for minutes, and that changes what is affordable. A gentle push applied for a decade can accomplish plane changes that no chemical burn could. Studies exist for solar polar missions using electric propulsion, and they generally conclude it is possible and slow. Solar sails are the more exotic version of the same idea, using no propellant at all, riding the pressure of sunlight itself. And a sail has one property that makes it uniquely suited to this particular problem, which is that its thrust is essentially free and unending, so the enormous velocity change stops being a budget item and becomes a matter of patience. Serious mission concepts for a solar polar observatory using a sail have been studied for decades. None has flown. The third approach is the strangest, and it is the one the video that started this conversation highlighted, and it deserves explaining, because the physics is genuinely counterintuitive. The cost of changing your orbital plane depends on how fast you are going when you do it. Change direction while moving quickly and you must fight all of that speed. Change direction while moving slowly, and it is cheap. In an orbit around the Sun, you move slowest when you are furthest out, which suggests doing your plane change far away. But there is a cleverer version, which is to dive first. Drop in extremely close to the Sun on a highly elongated orbit, and at the far end of that orbit, way out in the cold, where the spacecraft is barely moving, apply a small nudge to tip the plane over. The elongation does the work. A maneuver that would cost 94,000 miles per hour of velocity change from Earth's circular orbit can be made dramatically cheaper if performed at the slow end of a very stretched one. It is a beautiful piece of orbital mechanics, and it is the kind of thing that makes a genuine solar polar mission look plausible rather than impossible. But notice what none of these buy you. Every one of them is designed to observe the sun because that is the science case that justifies the expense. None of them is designed to fly far enough out, at a high enough angle, to photograph the whole solar system laid out beneath. To get the classroom picture, you would need to be both well above the plane and a very long way out. And there is no instrument that wants to be in that position. The sun missions want to be close. The outer solar system missions want to stay in the plane where the targets are. The photograph sits in a gap that no science case reaches into. There is one more possibility, and it is the one I would put money on, because it is how the first picture happened. Somebody will build a mission for another reason entirely, and it will end up somewhere useful with a working camera and nothing left to do. And an advocate will argue for turning it around. There are concepts under discussion for an interstellar probe, a spacecraft designed to head out of the solar system far faster than the Voyagers and study the boundary between the sun's domain and interstellar space. And such a mission would need to leave in a direction chosen for scientific reasons that might well be out of the plane. If one flies and if someone remembers to look back, we may get our second portrait from further out and higher up than Voyager managed. That is the realistic path, not a mission to take the photograph, a mission that happens to be in the right place and a person who insists, which, if you think about it, is exactly what happened last time. There was no pale blue dot mission. There was a spacecraft 32 degrees above the plane with its instruments about to be switched off forever. And one scientist who kept asking for years against people who reasonably pointed out that the picture had no value. He was right and they were wrong. And the thing that proves he was right is that you know what the picture looks like, and nobody remembers what the instruments were doing instead. So let us do the one thing we have not done tonight, which is to take the position nobody has ever taken. Not 32 degrees, not 17, directly above. Come all the way up with me one last time and look down at the whole thing properly. You are perhaps twice as far out as Neptune, and directly over the invariable plane, above the true middle of everything. There is no spacecraft here, and there never has been. This is the view from the illustration, and you are the first to have it. The first surprise is how little there is to see, and I want to be honest about that before anything else, because the classroom diagram lies in one specific way. It draws the orbits. Out here, there are no orbits. Orbits are paths, not objects, and paths are invisible. There are no glowing rings, no dotted lines, no labels. There is the sun, small and fierce and unmistakable at the center. And then there is a very great deal of black with a scattering of points of light in it, and nothing to tell you which of those points are planets and which are background stars, except that if you waited long enough, some of them would move. So, the first thing the true view would teach you is that the solar system is almost entirely empty, and that the picture we draw of it is a diagram of relationships rather than an image of a thing. We draw the orbits because the orbits are the point. Take them away, and our home looks like almost nothing at all, a bright light and some specks. But wait, and it assembles itself. Over hours, the inner planets shift, and the shifting is what reveals the structure. Mercury moves fastest, a small light hurrying around close in. Venus next. Earth, a pale point. And if your eyes were extraordinarily good, a second smaller point beside it that would be the moon. The two of them going around each other as they go around the sun. Then Mars, slower and slightly red. Beyond a wide gap, a scattered belt of far dimmer specks, and then Jupiter, moving with great deliberation, and, if you could resolve it, 4 small lights, attending it in a flat line of their own. Saturn, slower again, Uranus and Neptune so slow that over the course of a day they would not appear to move at all, and you would only know they were planets rather than stars by waiting weeks. And here is the thing that would strike you, watching from above, that no diagram conveys and no view from inside the plane could ever show. Everything is going the same way, all of it, without exception, among the planets, turning counterclockwise as seen from the north, in the same direction, at speeds that fall off smoothly with distance. It is not a collection of objects, it is a single motion, one great slow rotation, still turning with the spin of the cloud that made it. 4.5 billion years after that cloud came apart. From inside the plane you see planets. From above you would see the rotation itself, the thing that has been happening continuously since before there was an Earth to stand on. And you would notice the flatness in your body, in a way that no number conveys. Look toward the edge and everything is crowded into a line. Look straight down and it spreads out. Tilt your head slightly and the whole arrangement closes back into a strip. The system would feel less like a place and more like a sheet of paper with a light on it. And the fact that everything anyone has ever done happened on that sheet would be very difficult to hold in your mind while looking at it. Then look away, up, out, in the direction that is not the plane. And there is nothing at all. No dust, no bodies, no structure, just stars in every direction, out and out. The sun's whole family, all of it, is beneath you in one thin layer, and the rest of the universe is everywhere else. That is the view. Nobody has had it. Nobody currently alive is likely to have it. It is not a view of anything we do not already understand, and it would produce no discovery, and it would answer no question. It would only show us the thing we have always known, in the one way we have never known it, which is by looking. And if it is ever taken, that picture will be worth more than its science, exactly as the last one was. Now, as we finally come to the end of tonight's long climb, let us gather it all up and look at what it actually amounts to. Because I think this is one of those subjects that quietly changes how the sky feels once you have it. Everything you have ever known lives in a sheet. That is the summary. The sun, the planets, the moons, every asteroid worth naming, every spacecraft we have flown, every human being who has ever lived. All of it inside a layer so thin that on any honest scale model you could not draw it thick enough to see. And that sheet is not an accident. It is the fossil of a rotation, the permanent record of a cloud that fell inward 4.5 billion years ago and could only fall freely from above and below. The flatness of your solar system is the shape of its birth, still holding. We cannot leave it, not because it is far, but because we are already moving sideways at 67,000 miles per hour, and always have been. And everything we build inherits that motion before its engine even lights. Going up means fighting the inheritance, and the bill comes to more than any rocket we have ever built could pay. In 70 years of spaceflight, the only way anyone has ever climbed out is by asking a planet for a lift. 3 have managed it. Voyager 1, thrown north by a decision to look at a moon, which is why it was in a position to take the only portrait of our solar system that exists. Ulysses, which flew 1.5 years in the wrong direction to reach Jupiter, got thrown almost perpendicular and spent 18 years discovering that the sun has 2 winds, and we had only ever measured 1. Solar Orbiter, which is climbing a staircase built out of Venus right now, and which last year sent back the first proper look at the top of our own star, after every generation of humans who ever lived had looked at it from the side. And the picture on the classroom wall is still a drawing. All of them are. So is every image you have ever seen of the Milky Way, and that one always will be. We live inside 2 nested sheets, and we have never seen the outside of either. And we have mapped both of them anyway with total accuracy by watching things move and doing the arithmetic without ever once stepping out. So here is tonight's cascade, the thing to carry down into sleep. The solar system is flat because it fell because it was spinning. We are stuck inside it because we inherited its motion. We escaped it 3 times, always by borrowing a planet. We photographed it once by accident because someone wanted to see a moon. And the most famous image our species has ever made exists only because a machine happened to be leaning 32 degrees off the floor with nothing left to do. None of that is a story about limitation. All of it is a story about a species that could not get to the vantage point and worked out what was there anyway. And then, on the one occasion it briefly had the chance, remembered to look back at itself. And there is a small consolation hiding in the whole arrangement which I have been saving for the very end, because it only works once everything else is in place. We have spent tonight describing a view we cannot have, from a position we cannot reach, of a structure we cannot leave. But notice what the flatness actually costs us and what it does not. It costs us the photograph. It does not cost us the knowledge, because we worked that out anyway, from the inside, with arithmetic. It does not cost us the reach, because the same flatness is the highway that let us touch every planet. And it does not cost us the view outward, because the thinness of both our sheets is exactly why, looking up, we can see almost to the beginning of everything. Add it up honestly, and the disk has taken one thing from us, a single picture, and given us in exchange the ability to go everywhere in it and to see forever out of it. That seems, on the balance of the night, like a trade worth having made. Thank you for climbing out of the plane with me tonight, up into the one direction nobody looks. If sleep has been circling while we talked, let it land now. There is nothing above you that needs watching, and nothing below either, and the sheet we live in has been holding its shape without supervision for 4.5 billion years. And tomorrow night, or some clear night soon, when you happen to be outside after dark, you might try one thing. Find a planet, then find another, then the moon. Draw the line between them in your head and follow it across the whole sky from one horizon to the other. That line is the floor of everything. Everything you have ever heard of is on it or very near it. And straight up from that line, perpendicular in the direction nothing has ever meaningfully gone, the sky simply opens, thin and clear and empty, all the way out. You are lying on the floor of the solar system, looking up through the one clean window we have, at the one direction we can see forever and can never go. Sleep well, down here on the plane where everything is. Good night.